Thank you for joining us today for the webinar, Large Scale PFAS Risk and Management on Mine Sites. Before we get started, I'd like to acknowledge that I am hosting this webinar from the lands of the Whadjuk people. I also acknowledge the traditional custodians of the various lands on which you all work on today and the Aboriginal and Torres Strait Islander people participating in the webinar. So today's webinar is being presented by 360 Environmental and Howden Industries. So before we get started, I just wanted to cover a couple of housekeeping tips. Today's webinar is being recorded. We'll be able to share a link with you after the event is complete. We welcome you to revisit the content yourself and share it with your colleagues. Please put yourself on mute during the presentations. We'll be holding a question and answer session following the two presentations. However, we invite your comments and questions at any point. Please just type them in the chat box and we'll hold it for the discussion portion at the end of the event. Alternatively, feel free to raise your hand in the session and we'll address the question then. So today's presenters are Julie Powich, Principal Environmental Geoscientist at 360 Environmental, Michael Minter, the WA State Manager for Howden Industries, and Jake Reardon, the Technical Director and Co-Founder from Howden Industries. At this time, I'm going to hand the floor over to Julie, who's going to start today's presentation. Julie, it's all yours.
Thank you, Chris. I'm going to be starting our presentation today. We have a bit of a varied audience, so I'm going to do an overview of what PFAS is, why it's a risk in the environment, and then I'm going to look at the sources of PFAS in Australia that to date have been the usual suspects, just so you can get an appreciation of the scale of the risk that we're already examining nationally. And then we're going to look a little bit deeper at the sources of PFAS in mining, or what I like to think of at the moment as the unusual suspect. And from that, I will finalize with a bit of emerging risks for the mining industry before handing over to my co-presenters with Howden Industries. Just a disclaimer that my presentation has been prepared to highlight the emerging issues related to the use of PFAS in the mining industry. The pictures that are contained in this presentation are from publicly available sources to provide conceptual support and are not intended to directly represent any specific mining operations where PFAS is known or suspected to be present. So with that, let's jump into what is PFAS. For those of you who are not totally familiar with PFAS, they are a group of per and polyfluoroalkyl substances, which are a complex family of man-made fluorinated organic chemicals that have been produced since the mid-20th century. It's estimated at the moment to include 5,000 to 10,000 chemicals. These were originally used in the manufacturing industry as protective coatings. These are more commonly the group of perfluorooctanoic acids, or the PFOA compounds. And they were also originally used as architectural resins, known as PFNA. So just maybe before I go on, there's lots of PFAS-related acronyms, and for simplicity, I may just stick to them going forward. They all have very long chemical names. The secondary and more relevant components for the mining industry and much of the industrial sites that we have with PFAS in Australia are the aqueous film-forming foams. So these came about a bit later in the process. There are many different types of them. The original ones came about in about the 1960s. And they're the PFAS compounds. These are the ones that are particularly persistent and already have guidelines associated with them for environmental management. More recently, since the 2000s, the fluorotelomers, which include 6,2-FTS, 8,2-FTS, and a range of other FTS, fluorotelomer compounds, have come into effect. And these are maybe potentially the more softer components, but still have some persistence about them. So as you can see in the regulatory sense in this diagram on the bottom right, the PFAS and PFOA compounds had the initial attention. Some of the other ones I have listed are kind of in the early attention range, but guidelines are still being developed. And then because this list of chemicals keeps growing, all the other PFAS compounds that are identified are getting increasing concentration as time goes on. So why are we concerned about it in the first place? Well, the key risk to the environment comes from the fact that all PFAS compounds are highly persistent, bioaccumulative, and potentially toxic to humans and the environment. PFAS compounds are forever chemicals. They break down to other forms, but because they are synthetically manufactured and not naturally occurring, they never actually disappear from the environment once introduced. On top of that, PFAS is highly soluble and mobile, unlike contaminants like hydrocarbons, which are very strongly driven by flow rates in aquifers. PFAS compounds rapidly migrate long distances in a relatively short period of time as they disperse, and so they create much greater plumes in groundwater and in surface water bodies. Fun fact is that polar bears in the Arctic have PFAS in their systems at higher concentrations than any other chemical of concern that we've been investigating to date, including hydrocarbons, pesticides, and other metals. The other concerning component about PFAS compounds is that their toxicity occurs at very low concentrations, whereas most of the typical chemicals of concern that we have investigated previously as contaminated sites practitioners, we investigate in the parts per million range. PFAS compounds are toxic at the parts per billion range. Therefore, pretty much if you can detect it at the moment, it already potentially poses a risk. Humans are primarily exposed to PFAS compounds such as PFAS through food consumption and contaminated drinking water. For humans, the key compounds have half-lives of approximately 2 to 9 years within our bodies. Aquatic environments have a high level of bioaccumulative uptake. They have a lot of the compounds have relatively longer half-lives in biota and humans than PFAS. And edible aquatic organisms that have been studied have half-lives that are much shorter than humans, which is good and bad at the same time. As a result of these risks to the environment, over the last decade, PFAS has become a rapidly emerging contaminant of concern that has a high level of research and investigation happening globally. Just quickly with regards to that, we're probably a little further behind in our understanding of risk to human health than we are to ecological receptors. We're still learning about the health effects of exposure to PFAS, and studies indicate that the exposure to compounds could have some quite diverse impacts for human health. So in particular, females and infants are of greater risk and sensitivity to the accumulation of PFAS compounds, resulting in things like developmental effects, lower fertility, and lower infant birth rates. Additionally, PFAS compounds can interfere with the body's natural hormones and cholesterol levels and our immune system. Studies have already been undertaken in the last 18 months to demonstrate that that our response to antibody vaccines, such as that for COVID-19, are reduced as a result of PFAS exposures. We also have a reduced infectious disease resistance, which would be similar to the impacts on our immune system. And we also have an increase to the risks of several cancers, including kidney, ovarian, prostate, lymph system, and leukemias. So in Australia, quite a bit of attention has been had for many years on the occurrence of PFAS. The main suspects, or the usual suspects as I like to think of them, are related to the primary source being the use of these aqueous film-forming foams. And as a result, the majority of sites that are currently under investigation nationwide relate to defense sites, in particular in their firefighting training areas, airports, Department of Fire and Emergency Services, power stations, fuel refineries, and any sites with bulk fuel storage. Secondary sources from manufacturing and disposal of consumer products also contribute a lesser load to the environment. So manufacturing facilities that use PFAS compounds for their coatings pose a risk because we dispose of a lot of manufactured items in landfills. Landfills and waste disposal facilities have quite ubiquitous PFAS plumes beneath them. I can't think of a domestic landfill in the Perth metro area that doesn't have PFAS in its landfill leachate. Water treatment and sewage treatment plants are quite susceptible, and more recently we found that the land application of biosolids is quite accumulative for PFAS compounds as well, and this hasn't been largely studied to date, but the redistribution of biosolids creates a potentially large-scale emerging problem for us as well. The thing that the usual suspects all have in common is they largely represent point source areas of release. These two conceptual models demonstrate how you'll have a point source release either from a firefighting foam or water treatment plant or a landfill. And PFAS, being highly mobile, will migrate downwards into the groundwater table and into our surface water bodies somewhere downflow. Or alternatively, it will transport via overland flow into your surface water bodies. And all of those aforementioned things, sources, follow this general point source conceptual site model. As mentioned, PFAS in Australia is under investigation. There's about 520 identified potential source sites in Australia that, which the map on the left shows the distribution of. Within that, each state has a bunch of high priority sites. These are the ones where enough work has been done to be concerned that contamination is actually in existence and posing a risk to receptors. In Western Australia, there are 28 PFAS sites that are registered. Queensland has 19, New South Wales 43. Northern Territory's 3 sites are all related to defence sites. South Australia likewise has a couple of defence sites and a couple of airports, and Tasmania's sites are related to airports. So nationwide, mining is barely getting a mention on these sites of interest. Only 2 sites that I've been able to find are registered as contaminated and of interest, and they're both located in WA. But the other states don't have any mining sites that have even been registered on their radar at this point in time. So those usual suspects, they've been in the media a lot. We see quite a bit of this around. Locally, many of you are probably aware of the Bullsbrook class action in association with the RAF Pierce site, where toxic PFAS is in the water supply. There are Aboriginal and Indigenous communities who are filing class actions for risk of cultural loss as a result of the impacts to the aquatic ecosystems. And there are dozens of examples, of which these are just a few, that come up quite regularly. Until recently, though, until about a month ago, PFAS in mining has been silent. And then mid-April of this year, we finally got the headline in the West Australian: toxic chemical found in groundwater at BHP's Newman Iron Ore Hub in Pilbara. So for me as a contaminated sites practitioner, this is quite surprising because we've been looking at PFAS in mine sites for a bit longer than the last month and a half. You can tell from the sensationalism of this that PFAS in mining is going to be of rising interest going forward, especially when such a big player as BHP has finally hit the media. So the thing about PFAS in mining is the distribution and conceptual site model for PFAS is a little different than for our usual suspects. So drawing on my experience and my colleague Chris's experience in this area, the main point source release areas of PFAS in mining relate to firefighting training areas, which, unlike those on defense sites and in firefighting places, often are releases to unsealed ground over long periods of time that may be on the top of your open pit, on the side, or an old waste rock storage area. Not bituminized, there's nothing protecting you. The workshops. So while PFAS is being phased out nationally, many sites still hold large stores of AFFF on their sites with nowhere to dispose of it. And because people on site aren't aware of the risks of it, it's also still being used. Washdown bays are a big potential release area for PFAS compounds, water treatment plants, and 2 other suspects, the haul truck and the dust suppression truck. So our heavy vehicle haul trucks, most of them contain their own foam canisters, and the use and release to ground can occur anywhere: the pits, the haul roads, and underground. Likewise, dust suppression vehicles quite often use recycled water that's been impacted by PFAS from those point source areas, which then end up distributing the risk across the operational area. And that can include the haul roads, also along the conveyor lines. Obviously, that's not necessarily by the haul truck, but dust suppression along conveyor lines can also distribute compounds. And just from that generic mine site that I've pictured below, you can quite rapidly see how the mining issue is quite different to the issue that's faced from these smaller point source areas that have been investigated to date. And the reasons for this is because our diffuse secondary sources then become a large-scale issue. We have transported contaminated soils via the heavy vehicles through their tires, driving over contaminated haul roads from these primary source areas over other large areas of the mine site. PFAS impacted surface water runoff is entering sumps and dams. PFAS is impregnating concrete holding bunds and their underlying soils in the mine site infrastructure. Water recycling and reuse is distributing PFAS into processed water, water supply dams, and recreational areas. The standard water treatment units that are treating the recycled water are not equipped to process PFAS for the most part. Treated wastewater then releases PFAS back into the environment. So our biomax systems, our oily water separator systems, they're not removing the PFAS. And as a result of the fact that the sources aren't identified and we are recycling this water all across the mine sites, the cycle just recommences and the issue continues to grow. And so in addition to the standard point source release areas and the standard conceptual site model I showed previously, you can graphically get an impression here of how that distribution pathway becomes much more complicated in the mining environment and can be distributed over much larger areas to many different receptors that may not be otherwise recognized from the usual suspects. So that just brings me to my final couple of slides. Firstly, the key emerging risks that I see from my experience to the mining industry. Firstly, we're already seeing delays in the approval of mining proposals emerging in Western Australia. It's questionable whether other states are to follow, but I expect that they will. Currently, the onus is on proponents to demonstrate a clean water supply, the proponent is not impacting freshwater and potable water sources. It can be very challenging if you haven't really even been aware that you might have a PFAS problem and haven't started to investigate it. Linked to this, we've seen water abstraction license delays while these investigations have been underway. So source water becomes a bit of an issue. Obviously, mine sites are likely facing costly contaminated sites investigations to delineate the extent of impacts to soil, sediment, surface water, and groundwater. And then there comes the remediation issues. Currently, there are few on-site soil remediation options, and that means that mine sites will be facing a high cost of off-site disposal of impacted soils due to the large travel distances and few licensed acceptance locations to take that material. And then on top of that, and as will be the focus of Michael in the next presentation, mine sites are also facing even more costly remediation technologies to eliminate impacts to water supply to maintain the operations in scenarios where the sources haven't been treated first. So where you haven't removed the soil and your water continues to recycle around, it's really hard to remove the problem. And another issue that I don't think anyone's really been touching on yet is the potential risk that also then exists to PFAS in tailings dams. And I'm interested to see how quickly that comes to light. So where to from here? If you're with a mining company, I think we can expect that increasing regulatory pressure will be coming from mine sites to identify their PFAS risks. I think it would be in most entities' best interest to start including PFAS, the consideration of PFAS sources into all contaminated sites investigations. And you really need to think more about the pathways in the first instance than the sources, but reality is that the site history is often hard to determine, and because people weren't aware for so long that PFAS was an issue, the knowledge base on where it might have been used is really quite fuzzy. So you have to take a much broader view and work backwards to really understand where those source areas are. In the similar lines to that, early identification of potential sources, pathways, and receptors becomes critical to your investigation and to successfully delineating and remediating your site, and also to prioritizing where your efforts need to be put first. Also critical to this issue is understanding your water sources and flow paths. There's surface water, there's groundwater, there's processed water and recycled water, and they're all interacting, and those linkages need to be understood. Once you do get a handle on what the magnitude of your risk might be, if there's time, it's really important to manage the soil risks first. Otherwise, you're not eliminating the source, and the continued motion through the water supply continues. And then in addition, you need to consider potential remediation endpoints early. So analysis when you're looking at PFAS in your source areas will need to go beyond the older regulated PFAS sources and include the newer, shorter chain, less regulated carboxylic acid species, particularly if water treatment is a potential outcome. Well, we might not have guidelines for a lot of these things today. I'm sure in the next 10 years, we're going to see many, many more criteria and endpoints emerging. It's also important that we take the next step to do total oxidizable precursor assay analysis in order to understand the non-oxidizable components that have yet to degrade in these sources. Standard analysis really is only the tip of the iceberg. So on that note, I am going to hand this presentation over to Michael Mittner at Haldon Industries, and he's going to discuss for you some water treatment options and the emerging technologies in that.
Fantastic. All right, thank you for that, Julie. So the conversation now is going to move to discussing the management and remediation technologies available for PFAS impacted sites and the good management practices that are critical to ensuring effective treatment. So our knowledge of PFAS and the processes used to remediate these sites has changed rapidly over the past decade. As Julie outlined earlier, there are large variances in PFAS containing materials, and they are found in hundreds of products that are being used worldwide. At present, only a fraction of these PFAS molecules are regulated in Australia. Regulated variants are more typically found as legacy contamination, where older C8 AFFs have been used. The use of newer aqueous film forming foams, C6 and under variants, has increased the prevalence of the lesser regulated PFAS species. Now, as global understanding of the PFAS issue grows, so too will the list of regulated compounds. This is going to impact heavily on the mining industry, an industry that in remote locations is required to, in many circumstances, treat and reuse runoff and processed water for various mining operations. Understanding the prevalence of these chemicals on site early is critical in reducing the economic and environmental costs associated. So, when conducting these investigations on site, it is imperative that all stakeholders work together, both to ensure the scope of works is fully defined and that realistic discharge targets are set based on informed decisions relative to surrounding sensitive receptors. During this investigation period, it pays to consider how regulations may change in the future. The variance and discharge criteria requirements shown on the right reflect the health-based guidelines. However, guideline values on the left are based on adherence to the 99th percentile level of ecological protection under ANZEC. Variances like these can change the process flow to treat PFAS contaminated water in a huge way. Existing treatment options. Now at present, there are only a handful of technologies that are commercially available for the treatment of PFAS. These technologies include adsorption, ion exchange, ozone foam fractionation, and RO. It should be noted, however, that foam fractionation and RO have many shortfalls when considering large volume treatment systems with trace PFAS in the effluent and very stringent effluent criteria. Waste generation and effluent quality are the main ones. The only existing technology which is able to be implemented into an engineered, calculated and risk-free solution is adsorption and ion exchange. An added benefit is that through the combination of different ion exchange and absorptive medias, a tailored solution is able to be provided for each and every site application. So here I've provided a brief overview of a typical treatment system. The flow sheet obviously is dependent on the particular application, so this is due to change. So it starts with pre-treatment, typically employs existing oxidation and sedimentation techniques as required. It's important to get this pre-treatment stage right to maximise efficiency and downstream PFAS removal stages and to minimise waste generation. PFAS removal stages is the next stage in the sequence here, and this is tailored to suit the application. Influence of differing PFAS molecules makeup call for the use of different ion exchange adsorption medias in different sequences to provide the project outcome. Jake will jump into this and break it down a bit further in the next few slides. Post-treatment in the next stage, again, employs different treatment methods to achieve project requirements, i.e. disinfection for reuse, dust suppression and mining operations. At this point, we'll hand over to Jake Reardon and he'll break into a bit more detail regarding pre-treatment systems.
Thanks very much, Michael and Julie. Yeah, we'll dive a bit more into, I guess, the nuts and bolts of the PFAS treatment. Definitely starts with the pre-treatment stage. It needs to be effective and targeted, and by doing that effectively, you can suit long-term PFAS removal efficiencies downstream. Often surface water and environmental runoff will require vastly different pre-treatment to groundwater or runoff surrounding a hotspot or a source, for example. Non-mature contamination, such as what is usually surrounding new fire training grounds, may need an oxidation step. What this does is it helps to ionise non-ionised PFAS molecules, and that makes their removal downstream more effective. Some contractors or suppliers will use powdered adsorptive agents in the pre-treatment stage as well. That can be to remove co-contaminants, or it can be to remove bulk PFAS. This bulks up the waste, there's no doubt about it, because you're adding to the volume of sludge, which you then have to dewater and dispose of. But depending on the local regulatory requirements, it can actually help because you can immobilise the sludge while you're doing it. And that may mean instead of having to send it off to a lined landfill or even to incineration, you can dispose of it in a normal landfill. The most important thing to consider with pre-treatment is the waste disposal options, the project outcomes, the contamination makeup, and you also need to look at the local regulatory requirements. There is a lot of difference between each of the different states regarding disposal of immobilised PFAS cakes and soils into landfills. It's pointless doing something that might work in New South Wales and not work in Victoria or WA. So moving along, we'll dive into the PFAS removal stage. It's very dependent on whether we're in a hotspot with high level contamination versus a low level contamination scenario for, say, runoff. The lower level contamination is typically higher volume, such as in a mine site around haul roads. Areas with very old legacy contamination often need different types of resins to areas that have been contaminated with. Depending on the job, you will run the resin or the adsorptive media in lead lag scenario or multiple lead lag scenario. What that does is it ensures that lead beds load up as much as they possibly can, so that when they're ready for disposal, you're getting a good return on your investment. It's very, very important to run interplant sampling between each bed of media, and that can allow you to monitor theoretical loading capacities versus what you're seeing on site, therefore monitoring media health. It also allows for very successful cost and risk forecasting, which is a big thing for most clients or solution providers. You can definitely gauge when a bed is about to break through based on interplant sample results if they're done correctly. So I'll move along now to some waste generation information. So the most important thing is to look at viable receiving facilities, especially on mine sites, because usually mine sites are far away from everything. It's pointless setting up an ion exchange plant which uses liquid to regenerate the media if there is no liquid waste receiving facilities within a couple of 1,000 kilometres that you can get rid of that regenerant at. it might be better to look at other options. It is also very, very important to consider the sludge dewatering and what you're going to do with that, because as we all know, water treatment plants generate a lot of sludge. And if they're managed on site, quite often it might be worth making a lined cell for the waste that comes from the sludge, or you can reduce the volume as much as possible by not using inorganic coagulants and not using powdered adsorptive agents in the process flow, and then you can transport it to incinerator if required. You can minimise the waste generation that occurs at plants by tailoring each media toward the actual makeup of contamination that you're dealing with. This is very, very interesting when you come up to an application which has got a trace level of carboxylic acids and not many of the C8 variant, such as PFAS. You use a different type of resin, it's harder to get loading, so you have to run it in a different fashion so that you don't make too much waste. So with that in mind, we might look at some case studies. The first one here is a confidential mining client located in Australia. This one is particularly applicable to this presentation because it's a relatively high volume plant that treats up to 30 litres a second. We've treated around 200 megalitres on this project. It's ongoing. There's minimal pre-treatment required because the mine itself manages that, but the discharge requirements here are under 0.0002 micrograms per litre of total PFAS. As far as we are aware, it's the first and only plant in the country treating to this lower level, week in, week out, with no discharge exceedance. We've been able to do that by ensuring we use resins that are particularly suited to the molecular makeup, and we run them in a fashion that suits them to high loadings and also long lifetimes. We're very lucky on this particular project that there's limited co-contaminants to be concerned with. This means that the project is a lot cheaper than would otherwise be the case. And there's a high relative concentration of the less regulated carboxylic acids, which are typically harder to remove. But our client seems to have a long-term view in mind, and we have been directed to remove every single one of the PFAS molecules that can be detected, not just the regulated ones. An interesting piece to note about this plant, from contract signing to completion of the proving period was less than 2 calendar months, and that was during COVID. So we're pretty stoked with our team's effort with that. It's fully remote monitored and operated. People do visit it from time to time, obviously, but yeah, we can log in from all around the state, wherever we are at the time, on our computer or our iPhone, check that the plant's working. So we'll move on to a second case study here. This one is not really applicable to many mine sites. However, what it is applicable to is a potential hotspot on a mine site, such as an old fire training area. It's a slightly different project. It was a lot lower flow rate and a lot lower overall volume treated, only around 6 litres a second. But the total PFAS was particularly high, and the oxidizable precursors were of significant concern as well. So this particular project had a vastly different flow sheet to the last one. We've included an oxidation step up the front to help oxidize some of those precursors, get them into an ionized form, which can more easily be able to be removed throughout the media beds. There was a lot of solids on this project as well. So there was your classic coagulation, flocculation, and we also immobilized that sludge after we had removed it from the process flow. That allowed a lot of it to be removed to landfill rather than to incineration. This particular discharge requirement for this project was interesting because not only did it need to be under 0.002 total PFAS, but also for oxidizable precursors. And at the start of the project, the laboratories actually hadn't performed any reliable testing of oxidizable precursors down to that level. So we had to actually work with them to be able to prove the plant efficacy. A bit about waste from this project. There was 3 defined streams: a mobilised cake for cheap landfill disposal. There was about 30 tonnes generated, over 80 megalitres. There was lesser contaminated media for cheap landfill disposal as well. We didn't have to go for thermal treatment. There was about 9 tonnes of that. And there was only 4.3 tonne of heavily loaded media that required thermal treatment coming out of this plant. And I think if we'd been using purely liquid regeneration techniques for resin, we would have made nearly triple that volume of waste. And due to the actual location of this project, to get rid of that liquid regenerant would have been about 4 times the cost as what the solid waste cost us. Typically, the same price of a plant with trace levels will treat around 5 times the flow rate. So this was quite an expensive project, but the main reason was the heavily contaminated nature of the water that we were treating. As soon as the water goes down into the trace levels, yes, the flow sheet has to change a bit, but you don't have to have such intensive PFAS removal stages and the cost drops off. So in summary, I guess I'd like to say that all effective management of PFAS contaminated sites starts with proficient site investigation to determine the source and the extent of the plume. That helps us come up with long-term management strategies. Removing the source is critical to ensure effective long-term management. Quite often this is not done. In saying that, there is a big difference between a plant that's designed for runoff as opposed to a system that's tackling source contamination. Source remediation is mostly done with a small intensive system, whereas larger ones with higher flow rates are quite different. We really need to test for oxidizable precursors when we do the site investigations, both on the site and beyond the areas of concern. If they are present, there is a risk that the contamination isn't mature, and this will definitely alter the process flow required as the project progresses. It's easier to get it right at the start than to have to band-aid it in the future. Seasonal changes are also a big issue that we've had in the past. Insufficient understanding of the scope on both client side, consultant and contractor side at the start of the project can alter the influent water volumes and quality as we progress through the seasons. Ongoing selection of foams used on site are also going to play a huge part in the years to come, as we discussed earlier. With this in mind, smart decision making needs to be conducted around what foams you select and what systems you invest in for the treatment of PFAS. Moving forward, effective PFAS treatment systems will be systems that are modular and multi-barrier. Modifications to the plant flow sheets should be simplistic and not require a full redesign to be able to deal with possibly changing contaminants of concern, advances in laboratory capabilities and ever-changing regulations. So now I'll hand back to Chris and he can take some questions if anyone has any.
Thanks for that, Jake. Just as a reminder, if you have any questions that you've not yet submitted, feel free to pop them in the chat box or raise your hand and we'll get through as many questions as time allows. I might open the question session. So a question for Jake. Obviously, mine sites use a lot of water, especially over the winter months when, as you said, the seasonal variations in flows can often influence things. I guess PFAS treatment of water is all about contact time. Is there a sort of maximum throughput or output that would determine when the different technologies can least be effective?
That's quite an open-ended question, I guess. What I would have to say is that once you get over about 5 to 8 litres a second, it becomes quite hard to give a fully engineered and calculated solution that can run for a known amount of litres unless you're using adsorption and ion exchange. It should be noted that all of those particular treatment methods definitely do work. There's no doubt about that. It's just very, very hard to deal with variances in flow and contamination loading, and also stopping and starting with some of the others with ion exchange and adsorption. It's very easy to know if our contamination loading coming into the plant doubles, we know that it's going to last X amount, X amount of days or X amount of litres treated. Whereas, yeah, with some of those other technologies, it can become quite difficult just to react quickly to changes, I guess.
That's excellent. Thanks for answering that. It was a bit open-ended, so I appreciate it. Just waiting for some of the questions to come through.
Anyone from the floor want to ask a question?
Yeah, I'd love to. Thanks, first of all.
Quickly, so we know who's speaking.
Yeah, hi, Julie. It's Justin Lumsden here from Senversa. Thanks to you and Chris for putting on the presentation. Appreciate it. Look, I've got a bit of a comment and a question, if you like. First comment is really just about risk assessment. So a mine site setting is a very different setting and underlying assumptions to what goes into the NEP 2.0. So thinking about things like spiritual and cultural use of the land, particularly post-closure, thinking about things like household consumption, underlying assumptions for tier 1 screening levels versus bush tucker, and things like pastoral leases that often occur in those areas. So my point there and comment there is really getting the fundamentals right of a really robust risk assessment and conceptual site model before diving into treatment or management. And I think something that's of note there as well is some of the work that's been done into understanding ambient background concentrations of PFAS in the environments. You wouldn't think that would be too relevant to mining, which are often in remote areas, but certainly with some of the work that DWER has done in Perth Metro, they have found that PFAS concentrations are above freshwater 99%, ambient concentrations. So things like that could clearly be relevant to places like Port Hedland in Karratha. Don't know, I suspect they might be. So just getting that risk assessment bang on is the way to go before you jump into risk remediation management. I guess my question there for Jake, thanks, Jake, for your presentation, was really smouldering. So thermal destruction, is that something you guys have looked in and had experience and had comment on? I've seen some case studies on soil smouldering as a way of destroying PFAS and using granular activated carbon. So where you are doing that adsorption technique, using the GAC as a feedstock into the soil. Is that something you've got an opinion on or any experience on?
Look, to be honest, we do none of that ourselves, and I know that some of the science behind it works. What I will say is that only temperatures above 950 degrees have been proven to fully destruct and defluorinate these molecules. And I know that we send our waste media to various different thermal treatment disposal facilities. Most of them use rotary pyrolysis kilns. One of them is a plasma arc incinerator. And after speaking with them, I know that only the plasma arc incinerator gets full destruction. Now, obviously, we're talking here about highly concentrated material. It might be very different with more lowly concentrated soils and that kind of thing. Also, I know that different molecules have got different temperatures at which that they defluorinate. So, for example, the carboxylic acids are easier to strip fluorine off than what PFAS is, for example. So obviously that is going to change how effective something getting up to X temperature is. As for digesting it with soil, like you're saying, I've never actually worked with anything like that. I've had a little bit of experience with people that have, and I think it worked to a certain degree, maybe 50, 60% worth of defluorination, but I'm almost positive that it doesn't get all of the PFAS molecules fully defluorinated.
Thanks, Jake.
Thanks, Jake. Just, and I fully concur with the importance of the risk assessment and also of the understanding of the background concentration. So, as you said, we have our unpublished study for the Perth background, which is demonstrating there are concentrations, but that's a very and so very much in populated places and even regional populated places, this is a risk. Other reasons why it becomes important is DBCA may or may not have been using PFAS compounds in firefighting for bushfires. So depending on your environment, it can become important there. I think one of the challenges that we've been facing with the mine sites, maybe not quite being so aware of the PFAS risks, is that they're being faced with regulatory challenges on the permitting much faster than they can pull together that robust site, the robust risk assessment. And so at the moment, we certainly here take a fairly conservative approach, again, as I mentioned, with so few contaminants of concern in the PFAS suite actually being regulated. I think with considerations like cultural value of the land, pastoral use, all those things that don't have anything behind them, it's really hard to start discounting any risk from contaminants when they are found to be present in the PFAS suite, because inevitably 5-10 years from now, we're going to find many more of them are the focus of regulated guidelines and risk assessment and management remediation. Any other questions from our listeners today? Okay, well, with that, we might call it time. We have recorded this event as mentioned. If you have further questions, please do feel free to reach out to us directly outside of this meeting. And we thank you all for your time over your lunch break. It is great to be able to present to such a diverse crowd and really raise some awareness around this quite critical, potentially critical emerging issue for the industry. Thank you so much.
Thank you very much, everyone.
Cheers.
Thank you.
Thanks.